Hello, everybody. This is another video compiling our latest science adventure. This one on the subject of electromagnetism. So there are only four forces in the universe. There's gravity, the electromagnetic force, and the strong and weak nuclear force. The electromagnetic force probably has the biggest impact on our everyday lives. So gravity affects us, of course, but it mostly dominates on a large scale as the force of attraction between planets and galaxies. The strong and weak nuclear forces dominate on very small scales at the atomic level. The electromagnetic force, however, is always affecting us in our interactions with everything. Here's a diagram of an atom, a most basic particle that makes up everything. Its particles have charges, positive and negative, and some are neutral and have no charge. Electrons, with their negative charge, are central to electricity and magnetism. Electrons are on the outside of the atom, and they repel each other. You've heard the phrase opposites attract. Well, that's true at the atomic level. Positive charges attract negative charges, but the opposite is true as well. Sames repel each other. And so negatively charged electrons push other negatively charged electrons away. So this is pretty fascinating when you think about it. When you push against a wall, believe it or not, none of the particles in your hand ever touch any particles in the wall. That's because the negatively charged electrons in the outermost parts of the atoms in the wall are repelling the outermost electrons of the atoms in your hand. There will always be a space between your hand and the wall. What you're feeling isn't the particles of the wall itself, but the repelling force of the outermost electrons of the wall. So in this painting, the fingers won't actually ever be touching each other's particles. There's so much empty space in the atoms we're made of that if we reduced ourselves to just the mass of the particles in our bodies, would be reduced to the size of a grain of sand. But you say it looks like we're solid, but looks can be deceptive. At home, we like to put different things under a microscope. And we looked at the cover of this Percy Jackson novel. And it looks like the Percy Jackson character is drawn in solid colors. But when you look at it closely under the microscope, you'll see that it's composed mostly of empty space to save ink. But from a distance, it looks like the painting is printed in solid colors, but looks can be deceiving. And as Sophie says,
I'm actually levitating.
Now, getting back to our subject, when electrons line up in a certain way, they create a system of repelling forces we call a magnetic field. In many materials, the magnetic fields are pointing in all sorts of random directions, and they cancel each other out, and there's no force acting in any particular direction as a whole. But in certain materials, called ferromagnets, all the spins and the orbits of the electrons will line up and reinforce each other. That is, they have the same magnetic orientation, causing the materials to become magnetic. This would be your normal iron, cobalt, nickel metals. These are kinds of magnetic, the magnets that people love playing around with. Magnets have two poles, a north pole and a south pole. The magnetic field is represented by field lines that start at a magnet's north pole and end at the south pole. They look like this. The magnetic force is caused by the magnet's magnetic field and points in the direction of the field lines. If you have two magnets next to each other and their north poles are facing each other, or their south poles are facing each other, you can see that the field lines move away from each other. So you feel a repelling force between the two magnets. Here you can see Davis setting up two donut magnets on a pencil with their same poles facing each other. The top magnet seems to levitate as it's repelled by the magnet below. And if you put the north pole of one magnet next to the south pole of the other, then the field lines go straight from the north pole of the first magnet to the south pole of the second, and you feel an attractive force between the two magnets. This is why opposite poles attract. So here Davis flips the magnets over, so their opposite poles attract each other, and they stick together. You can see these magnetic fields yourself if you get some tiny iron shavings. If you sprinkle them on a piece of paper, they just fall straight down. But when you put some permanent magnets under the paper, and then you sprinkle the iron shavings on top of the paper, you'll see that the iron shavings fall into a pattern where you sprinkle them. It's the same pattern I showed you in the previous diagrams showing the directional lines of a magnetic field. Earth's magnetic field, also known as the geomagnetic field, is the magnetic field that extends from the Earth's interior out into space. The magnetic field is generated by electric currents due to the motion of molten iron in the Earth's outer core. The Earth's magnetic field allows a compass to work. A magnetic compass is the most familiar compass type. The needle is magnetized, so the north pole of the needle points to the Earth's south magnetic pole, which is on top of the Earth. The needle is mounted on a low friction pivot point so it can easily turn, and when the compass is held level, the needle turns until after a few seconds to allow oscillations to die out, it settles into its equilibrium orientation. By the way, during our research, we found out that the great scientist Albert Einstein said he was fascinated by the first compass he was given as a kid. And then later, when Einstein was a patent clerk working at an office that analyzed new inventions, he said he was fascinated by the sorts of electromagnetic gadgets that were being invented at the time. This inspired him to perform his greatest works. Now let's move from magnetism to electricity. We need to know something about electricity before we can learn more about electromagnetism. Let's start with static electricity. That means electricity that isn't moving around in a current, but just staying in one place. Here you see Davis rubbing a balloon on Sophie's hair. When he does that, some of the electrons in the atoms in Sophie's hair actually rub off onto the balloon. That gives the balloon more negatively charged electrons. That overabundance of electrons on the surface of the balloon then makes it attracted to the protons in Sophie's hair because protons are positively charged. If too many electrons build up, the extra charge can be released as a spark. In the air, those extra charges can result in lightning. The bottom parts of thunderclouds are negatively charged, and they discharge on the relatively more positively charged ground. Now, metal has very interesting properties insofar as their electrons are concerned. The electrons of metals aren't held to the nuclei of their atoms and are allowed to roam freely. That allows metals to create electric circuits in which electrical currents flow. The permanent magnets we've been using so far are made of metal. We can therefore use magnets to exert their magnetic fields on metals and make the electrons of the metal move around to create an electric circuit. So if a loop of metal wire is moved through a magnetic field, the magnetic field starts to move the electrons around the metal wire in the same loop. This flow of electrons is what we call an electric current. The more loops of wire you have, the more current you generate. You just need some way to keep moving the loops of wire through the magnet. With that in mind, electricity can be made in the following way with an electric generator. We used a hand crank electric generator. You crank the crank around, which moves lots of loops of copper wire inside a magnet. The magnet moves the electrons in the copper wire around through the metal circuit, which leads to two small light bulbs. It works like this. There are metal contacts here. Now what's going to happen is this crank, when you crank it, it's going to turn what is in there. What is that?
Copper wire.
Copper wire coiled around and around. That's just metal, right? But it's metal that allows electricity to electrons to flow through very freely. What's this around it?
Plastic case, plastic case.
What do we?
Magnet.
It's a magnet. This is actually a magnet around it. So all we have here is a copper wire and a magnet around it. Now, what this is going to do is there's going to be electrons that are going to be flowing around here. What's that?
Which way do you spin it?
You can spin it either way. Now, when you spin around this wire, it interacts with the magnetic field to make the electrons flow around, and they flow through this metal to one of these two lights. Now, believe it or not, there's no battery in here. It's not plugged into the wall. Do you think it's going to be magic if we get those light bulbs to light up with no battery and no plugging into the wall? So, Davis, why don't you give it a crank? Go one way first, real hard.
How should I hold this?
And look, that light is going on, the red light. See that red light? Now wait, stop. Now try the reverse direction. Yes, and now it's going the opposite direction. Now, in our case, we crank the copper wire around with our hand crank. But you can use lots of different ways to turn around copper wire in a magnet to create electricity. You can use the wind. When the wind turns a wind turbine, it's turning coils of wire in a magnet inside the wind turbine and creating electricity. Water power can be used to turn coils of wire in a magnetic field. Coal and gas and uranium can create heat to generate steam that creates pressure that moves metal wires in a magnetic field to create electricity. You can use just about any energy source to spin the turbines, but the different ways to generate the movement of the turbines have different costs and benefits, of course. For example, to produce 1 gigawatt of electricity, it takes the following to do it with different ways of generating electricity. You can see that some types of fuel take a lot of tons per day, but others, like solar and wind, actually take a lot of space because they have to take up a lot of land to produce the same 1 gigawatt of electricity. Some of these ways of producing electricity cause some pollution. Other ways produce less pollution, but require large amounts of land to be directed to the sole use of producing energy, to the exclusion of land used for other things like growing food or housing people. But whatever the fuel used to move the turbines, your appliances pull out some of the electrons sent to your house through the electricity lines that provide electric current power to the appliance's motor. So now that we've looked at how electricity is generated, let's look at how electricity can be used to create machines that do useful work for people. And that's in the form of a motor. The flowing of electricity through wire generates a magnetic field. But what makes a motor is that it adds another magnetic field in the form of an actual magnet to the magnetic field produced by the flowing electricity through the wires. Those two magnetic fields repel each other and cause a motor to turn, which can then turn wheels and anything else to do work. One of the great discoveries in history was the discovery that two magnetic field forces pushing in opposite directions create a force moving outward. There's really no intuitive explanation for this. I can't give you an analogy to real life that will clearly explain why this happens, but it does happen. Let's see. You take a battery and you stick a magnet underneath it. Then connect the positive end of the battery to the magnet. In this very simple motor, the current flows downward on both sides of the wire, and the magnetic field is pointing outward when it reaches the wires on the side. Now, here's how we did it. There's the battery. We put some strong magnets underneath it, and then we put a copper wire on top of it, bent into a heart shape. We did that because we love science. Well, we do love science, but really the heart shape is just a shape that's symmetrical and balances easily on the battery. Now, watch now how the magnetic field created by the current flowing through the copper wire from the battery interacts with the magnetic field of the magnets. We did it with an even bigger battery too and got an even bigger result. Now, this diagram shows the direction of the magnetic field with red arrows and the direction of current with blue arrows. Again, the magnetic field is pushing up towards the battery. The electric flow of current is pushing down towards the magnet, and those opposing forces cause an outward motion on the wire, causing it to spin around the magnet. Now, I want to show you a video of me explaining what's called a Stirling engine, named after Robert Stirling, who invented it in 1816. It's a simple but fascinating machine that works when you put hot air underneath it. A Stirling engine shows how heat energy can be used to create a cycle in which a wheel is turned and work is done. I'm going to put the hot water there. I'm going to put this on top. Now what that's doing is heating the air under this pump. There's a little kind of a plunger thing, and pretty soon what's going to happen is the bottom is going to be hot, the top is going to be cooler, and you know heat expands, it makes the molecules jump around, right? Heat imparts energy, right? And when the energy is in the bottom part of this and the air gets hotter, the molecules are going to bop around a lot, and they're going to exert some upward pressure on this plunger. And if which way does it go? I think I do it this way. If I apply just a little momentum to this, that will go for like 7 minutes. Now what is happening is the little momentum I supplied at the beginning pushes one of the levers down, and that pushes the plunger down. The heat
speeding up
pushes it back up. That gives the wheel a little bit more momentum, and that pushes it down. And it will just keep this cycle going for as long as the bottom is hotter than the top. And in fact, you can increase the difference in temperature between the top and bottom of the engine, and therefore increase the difference in the pressure in the top and bottom by adding ice to the top. Now, as you can see here, when you do that, the wheel spins even faster. Now let's see how electricity and magnetism improved upon this technique to create a similar cycle that also moves a wheel. This method uses the same principle that made the copper wire move around the battery that was on top of the magnet we saw earlier, but it shows that principle at work in the form of a motor, which we're all much more familiar with in our daily lives. So Davis used a kit to make this simple motor, and it's a great way to see exactly how a motor works. Here again, we have two magnetic currents working together to produce a moving force, a force that in this case drives a motor, which in turn can move anything else we want it to move. Okay, so we finished making our basic electromagnetic motor. So I've hooked it up to two 1.5 volt batteries, AA batteries. And they're connected to this circuit here. You got the magnets here, you got the copper coil in the middle, you got the copper here touching the little cylinder here. So what I'm going to do here, bud, is connect the circuit, connect these two batteries here. Now, nothing has happened yet because you have to start the cycle. Can you just put a little tiny twist on that? There you go. You started the cycle, and now the electricity flowing through the magnet is keeping the cycle going. And now, if we disconnect the electricity, it stops.
So
Now, it won't start going again until I start applying the electricity. The battery's providing the electricity. You ready?
Mm-hmm.
Okay. There it goes. And now look. What happens when that spins is it's attached to a pulley system. So if you were going to use this to power something in a factory, for example, you would attach cables or ropes to that, and that would move something else that would move either, you know, a wheel or a turbine or something, and you'd power it. Oh yeah, there's the electricity.
Oh, I see it,
sparks coming out of the copper connector. That is pretty wild. Now, I want to show something here on the video. There's an occasional break in that circuit. See that metal? Mm-hmm. The cylinder? See how it has an opening in it? Mm-hmm. Right? That cuts off the electric current for just enough time to keep this cycle going, which I'll explain in a second. So here's another graphical way of showing how the commutator part works. As we know, the copper wire coil in the middle acts as a magnet when it's spinning, and it has a north pole and a south pole, indicated in red and blue here. The south pole is attracted to the north pole on the left side, and so it turns toward it. But once it passes the north pole of the outer magnet, it will start to turn back toward it unless the current is stopped temporarily, which is what the commutator does. Here we see the current is turned off, so the copper wire coil magnet continues to turn, pushed ahead by its momentum. The part called the commutator is that rotary electrical switch that periodically shuts off the electrical circuit that creates the second magnetic field. By doing this, it allows the motor to continue moving with the same sort of angular momentum that drove the Stirling engine we saw previously. And it pauses the current just long enough to move forward and then pick up the magnetic field again when the circuit's reconnected, driving the motor further around. This cycle continues, creating a steady rotating force. So Davis and I took apart an actual appliance, a fan, to see if the motor inside it looked like what we built. All right, hey, Davis is taking a video here. What we did is took apart an old fan. Still works, but it wasn't a very good fan anyway. Took off the casing, and in here is an actual motor. Now look how similar it looks to what we built. We have, instead of a battery supplying the power, we have the electricity. It's plugged in out here into an extension cord. And I'm going to turn it on now, and we'll just see if this works. There it goes. Now, as you can see, the electricity is coming in here, and just like our internal motor, I mean the motor we made inside, you can see that the copper wire is going in there. And it's probably set up in a very similar way to the motor, electric motor that we made. And I think what I'm going to do is try to, you know, unpack this a little bit more, take it more apart, and we'll see just how similar the inside of this motor looks to what we made. Well, sure enough, we open this up a little bit more. There's this housing where the fan blades went in. And then here, I had to unwrap some stuff, but here is all of the copper wire wound round and round and round to create that part of the magnetic field that helps power the motor. And also, I think this part here, where you see the gaps in the metal, that is the commutator that occasionally shuts off the magnetic current so that the magnet won't start moving backwards and the momentum just keeps pulling it forward over and over and over again. We also like to take apart old busted electronics and turn them into robot art. Here we use the packaging materials for a television and turned it into a robot body. Then we hot glued a bunch of old parts on a styrofoam head. As you can see here, we preserved that fan motor on this female robot's forehead so Mom could see it every day out the window when she's in the kitchen. So many things we use work with motors. Here, Sophie and I use some kits we got to make a variety of simple motors that do all sorts of things. This one turns a fan and a wheel of bubble wands, which the fan blows air through to blow bubbles. This one turns a propeller that moves a car forward. And by the way, I also want to mention how this electromagnetic dynamic makes a speaker work too. We've taken apart a bunch of speakers in the past, and we're really interested to see that there were magnets and copper wire in the speaker parts. Well, a speaker takes electrical impulses that indicate different sounds, creating a magnetic field that interacts with a magnet, which makes the speaker vibrate in a way that pushes the sound waves to our ears. Now, one thing we haven't explained yet is how a battery produces electricity. We used a battery in a couple of our previous demonstrations, so let's take a moment now to see how a battery produces electricity. Essentially, a battery has a positive end and a negative end. Not surprisingly, based on what we've learned, these ends are made of metal. Once you have a positive metal end and a negative metal end of a battery, all you need now is something in between to transmit an electric current. A battery uses special chemicals to do that, but you can actually use fruit juices to do it too. This is how it works. The positive end, in this case some copper, is positively charged, and the negative end, in this case some zinc, is negatively charged. And the electrons move from the negative charge to the positive charge through the fruit, which has the properties of an electrolyte, which is a fluid material that allows an electric current to pass through it. We did this ourselves at home. I connected a tomato and an orange together at first, but the light didn't light. So I added a kiwi fruit, and lo and behold, the light actually started to flash on and off. We made a battery out of positively and negatively charged metals, some wire, and fruits that acted as electrolytes to transfer the electrons, making a current that powered the light. So we've learned a bit about electricity and magnetism and motors. And to wrap up, I want to put all this stuff in some larger historical context. Let's go back now and remember the Stirling engine. Before electricity was harnessed for work, people figured out how to turn heat into work. So the most important invention in human history really was turning heat into work, which happened around 1700. Then later, electricity and magnetism were discovered to be able to do work as well. Now, these discoveries revolutionized the life of humans on Earth. They gave rise to the most dramatic increase in well-being and human happiness the world has ever seen. Just look at this chart. It shows how gross domestic product, that's the value of all the goods and services that benefit people, skyrocketed after the Industrial Revolution. For thousands of years, the world population and gross domestic product per person remained essentially flat. I mean, your quality of life in 1700 wasn't much better than your quality of life would have been in the year 200 or 200 BC. But then people's quality of life took off like a rocket after the Industrial Revolution. As Harvard professor Steven Pinker, for example, has pointed out, gross domestic product, quote, correlates with every indicator of human flourishing, including longevity, health, nutrition, peace, freedom, human rights, tolerance, and even self-reported happiness levels. Following charts show the many ways the world has improved for the better following the Industrial Revolution. Just look at how much after the Industrial Revolution life expectancy increased and how quickly people rose out of poverty. I want to use one example of how the ingenuity spurred by the Industrial Revolution dramatically improved our lives through the light bulb. The big advance here, of course, was when Thomas Edison turned electricity into heat that makes a filament white hot to create light, but doesn't break when it's heated. Thomas Edison experimented with thousands of materials before he found one that could heat up white hot without quickly burning up. He even tried hairs from the beard of his business partner. Ultimately, he found that a kind of bamboo, properly treated and carbonized, would do the trick. When Nobel Prize winner William Nordhaus traced the history of lighting during the past 2 centuries, he concluded that we vastly understated its impact on our standard of living. For example, George Washington calculated that it cost him more than $1,000 in today's money to burn a candle for 5 hours a night for a year. But as technology improved after the Industrial Revolution, people had to work less and less to pay for the light needed to read or do anything else at night. This chart shows how the price of lighting went way, way down after the Industrial Revolution. And just look at how fewer hours people had to work to pay for light as technology improved. This chart shows by year how much the average worker had to work to make enough money to pay for 1 hour of enough light to read for an hour at night. In 1800, you had to use a candle, and the amount of time needed for the average person to work to illuminate reading at night for 1 hour was 6 hours. Back in 1800, the average worker had to work 6 hours to make enough money to buy a candle to read at night. But in 1880, kerosene lamps were developed. Then the average worker only needed to work for about 15 minutes to pay for the energy needed to read a book at night for an hour. In 1950, with the incandescent light bulb, the average worker only had to work 8 seconds to be able to read for an hour at night. And today, with LED lights, the average worker only needs to work 0.33 seconds, third of a second, to make enough money to create enough light to read for an hour at night. And the results of the Industrial Revolution keep producing more and more improvements and technologies that improve people's lives every day. So that's it for this week's science demonstrations. If you enjoyed it, pass it on to others who might enjoy it too. See ya.